So now that we've taken a look at a Memoizer and how to design it, how to implement it, let's see how we can apply our Memoizer to our PrimeChecker app. And this will also give us a chance to talk about how to apply the Executor Completion Service to the PrimeChecker app as well. So we're going to get kind of two for the price of one here. So again, same basic thing as before. We have our PrimeChecker app, which is going to use the Executor Completion Service and a Java 8-based Memoizer to check to see if n random numbers are prime. Same semantics as before. It's embarrassingly parallel and it's compute bound. We're going to have a cached thread pool this time, just for the heck of it. We don't have to, but it was just something to add. So keep in mind that cached thread pool works as follows. It starts out with there being no threads in the pool, and then as requests come in to execute work, a new thread will be created on demand if there isn't already a thread available that's not in use. If a new thread is created, it'll do the computation, and then it sticks around for a while, a minute. And if new work comes in while the thread is still alive, that thread will be used to run the new work. If after a minute nothing comes in, then that thread will be terminated. So that's basically the semantics of a cached thread pool. So we're going to use a cached thread pool to do the computations. Here's the PrimeCallable class. This is the class that does two-way calls to see if a number is prime, and it returns 0 if the number is prime, or the smallest factor if it's not prime. So you can see that it implements the callable interface, so it can run in a thread pool. We parameterize the function that we're going to have. So this is the PrimeChecker function that we're going to use. We'll see how that works in a second. And that's passed in as a parameter to the PrimeCallable object, and it gets stashed away. And this is the new thing that we added to this. We didn't have this before. We hard-coded the function. We hard-coded it to be the brute force function. And then this is the hook method that's called in a thread in the thread pool. And as you can see, what it does is it goes ahead and calls the apply method on the PrimeChecker that's stashed away from the constructor, and that figures out whether the number is prime. And that allows us to be able to parameterize different prime checking algorithms without changing this code. We can parameterize it here by passing in a different function to the constructor. The result that comes back from call is a tuple that keeps track of the original number, which is the prime candidate, and the result of doing the computation. Here's the main activity. This creates a Memoizer that's going to be used to optimize the primality checking for up to count random numbers or exactly count random numbers. And this is basically what it's going to look like. So here's the start computations method, which runs in the main activity. And what it does is it makes a new Memoizer, which is going to be used for caching results. As you can see here, we can either have the brute force checker, or we could put in a more efficient checker if we wanted to. This is a good example of the behavior parameterization features that are supported with Java 8 and beyond as the result of method references and lambda expressions and so on. We also give it a concurrent hash map so that it'll do the appropriate compute if absent methods, which is a check then act atomic method, correctly and efficiently in a multi-threaded program, much more efficiently than would be the case if we were using, say, a synchronized map. Here's the main body of the code. We create count random numbers in this range, which will ensure that we have duplicates. And then for each random number, we're going to go ahead and make a new PrimeCallable instance with that number and the Memoizer. So you can see the Memoizer up there. We pass the Memoizer in, which will then be used to do the computation. So if you think back at what PrimeCallable looked like back over here, you'll see that we passed in a function, and that function was what was used to check to see if a number was prime. And then over here, we cleverly pass in a Memoizer, which is going to be parameterized by the way in which we check to see if a number is prime or not, and is also going to have this memoization feature where it'll store things in the concurrent hash map, allowing the numbers to be looked up as necessary. So The cool thing about this is completely transparent to the PrimeCallable. If we decide for whatever reason we don't want to use memoization, we can just pass in the efficient checker or the brute force checker as the second parameter to the constructor. And PrimeCallable is none the wiser because what's being passed in here is a function. And as long as it has an apply method, it'll do the job. And as long as it does the job correctly, that's fine. This is just a way to do transparent optimization. So again, a Memoizer can be used wherever a function is expected, so it makes the behavior transparent. Then the last thing we do is for each of these PrimeCallables in the stream, this is a terminal operation, we're going to go ahead and execute use the executor completion service to submit that PrimeCallable for processing in a thread in the cache thread pool. So we're going to use the submit method. This is a method reference. We're going to go ahead and submit this thing, and this will submit this value returning task because that's what the PrimeCallable is. It's a value returning task. We're going to submit it, and then it'll go ahead and be processed in the background by some thread in the thread pool. And the cool thing about this, if you go back and you look at the executor service implementation, which I think we looked at last week, you'll see that we had to store the results in a list of futures because we were using the executor service, and its submit method returns a future. Now that we're using the executor completion service instead, we're able to leverage the fact that the executor completion service has its own internal queue. And so as a result, we don't have to store these futures ourselves. They're actually stored in the executor completion service, which greatly simplifies the code logic and allows the results to come back more efficiently. Speaking of which, we have to go ahead and create another thread. This is going to run in the background, and this is going to be a thread that's going to run something called CompletionRunnable. We'll take a look at CompletionRunnable in a second. And what the CompletionRunnable thread will do in the background is basically use the completion queue that's part of the executor completion service to get the results as they finish and print out what the results are. So we make ourselves a new CompletionRunnable, and we go ahead and make a new thread that uses that CompletionRunnable as the parameter here. And then we go ahead, and start that thread. So that'll start something running in the background, and that will then wait for the results to occur. Here's the CompletionRunnable class, which implements runnable, which means, of course, it has a runHook method. And here's the runHook method. It iterates through all the results, and we're going to have as many results as there were requests. So there was mCount requests, so we're going to get mCount results. And while we haven't finished iterating through all the results, we're going to go ahead and call ExecutorCompletionService. That's the method, that's the field that keeps track of the executor completion service that we initialized. And we're going to call take followed by get. Now, what's interesting here is that take will block until there is some completed future on the internal completion queue available. And once take returns, then get will be used to convert the future that comes back into the actual prime result, which is what the future is encapsulating. So in this context, take might block, but get will not block, because you don't end up in the completion queue unless you're completed. And then when we're done with that loop, after we get the next result, we check to see if it was prime or not, and we print the right result, we print the right output here. Here's just a little Androidism. We're going to want all these computations to keep running even if you rotate the phone. And to do that, we stick everything into this retained state class. So we have the executor completion service, the executor service, the CompletionRunnable, the thread, and the Memoizer all stashed away in state that's retained. And that way, when you rotate the phone, all that state remains active. It never gets destroyed. And only the visualization changes, but the actual computations continue to run in the background. So that's an Androidism, but it's a cool thing to know about if you're programming applications that have to run on Android and want to keep computations running in the background while you rotate the phone. Okay, that is the end of the PrimeChecker app discussion. This is pretty cool, and this will come in useful for assignment number 3, when we're going to switch from using the executor service to using the executor completion service.